Hi everyone, welcome back to the channel. So from the last couple of days or weeks maybe I was not available on this YouTube channel because I was very busy with some work. But finally I got some time and I'm back today. So I thought let's make a video which I think is very important when you are working on a like distributed system. So a very common issue with the distributed system is how data flows. One of the common problem with distributed system is the concurrency bugs, and it happens quite frequently, and you'll never know when it can occur. So today we are going to talk about some of the actual concurrency bug that makes your system fail, and you don't even realize until it happens in production. So concurrency bugs don't come from a obscure edge cases. So people think that it will come from the edge cases, but in most of the cases it comes from a very it's basically about how the flow runs and how the time and shared data, shared state talk to each other. So what's make them dangerous is not about the complexity of the code that you have written, but it's more about how it behaves. So most concurrency failures aren't caused by exhaustive hardware behavior or a memory model. They come from the code that looks clean, logical, and obviously correct until the CPU scheduler find it one interleaving you didn't even think about. So in today's post, we will do a very deep practical breakdown of most common concurrency bug found in a real production system. So this is based on a book which I was reading. From that, there is a chapter called Common Concurrency Problems, and study by this guy across MySQL, Apache, and Mozilla and OpenOffice. So the focus of this blog is the bug pattern that actually shows up in production. Why this happened, not just how, and how to fix them correctly, how to explain them clearly in your next interview or design reviews meetings. But you might be thinking, why does it still matter when we are in 2025 or maybe 26, which is coming from next week? Why are we still thinking about this? Because now we have Rust, which is very concurrent safe. We have Go. We have many concurrency languages, right? Which are safer. We have async await, we have actor model and better libraries to do so. But if you think about it, still the production system continues to fail in a very familiar manner. So because that's not about how these things actually prevent. So for example, async does not remove the concurrency, it basically hides it. When you go deep inside, you'll find it async calls are actually hiding the concurrency bugs. Thread safe data structure don't predict high level invariants. Lock-free code reduces your blocking but not the complexity. So distributed system quietly reintroduce shared state via caches and queues, which will be gonna cause some issue in future. So modern systems they don't crash very many often, but they actually fails more silently, which is very rare to find. And when you try logging it, you won't be able to repro because that happens based on some very specific scenarios, mostly with the heavy load or some like race condition issues. So how this is based on the blog is based on the 105 real concurrency bugs studies in a very mature code bases that basically revealed very two important factors. So the 70% of bugs were not deadlocks, and 97% of the non-deadlock bugs fail into two patterns, just two patterns. So most engineers, basically we all have studies about deadlocks in our operating system classes in our college. So we always worry about the deadlock first, but the real failures happen with due to atomicity and ordering mistake. So before diving into, we should have a very clean mental model. So what the mental model is, like how human things are actually sequentially. We read code from series of steps like first do A, then B, then C. The CPU does not see the same structure. It always wanted to optimize its execution. So it sees interleaving, reordering, and context switches at the worst possible time just to optimize its availability. So a very useful rule of thumb that I would say you should have is, if your code can break under some execution order, your scheduler will eventually find it. So let's start with the very first one, all the non-deadlock bugs, which are basically causing the silent failures. In that case, they don't like show up in your system, but they silently corrupt your state or maybe crash occasionally. And but you won't be able to find it when you add some logs because they disappear. So so let's start why it's getting caused, right? So first of all is the atomicity violation bug. What atomicity basically means, you might know about acid property. So atomicity is basically about like keeping everything into one atomic manner. So for example, if you have like 10 steps, you want everything to be done within one single step. So for example, everything should be atomic. So a sequence of operation is intended to behave as one unit, but the program does not enforce it, then you will see this atomicity violation bugs. For example, if you have a thread like this, so you have two threads in your computer. One is actually doing this. If ptr is not equal to null, use this ptr. And in thread 2, you are actually assigning ptr to null too. ptr to null. Assume at the t1 you did this check, and at p3 you actually use the ptr. But before that, at some time t2, you actually got this. I will explain it more clearly. So for example, at time t1, you read the ptr and find it, okay, this is not null, so I'm gonna use it. Okay, at let's suppose t3, but in between at t2, some other thread actually assigned the ptr to null. So now this is causing an error because ptr is null and you are using a null value, which can crash your system. Why this bug is very dangerous? Because when you look at the very first glance, it looks very clean and obviously correct, and it only fails under very specific time, rare to test, and it's very common in production. A very simple fix can be using lock. So you can apply a lock and put everything inside. So until unless this thing is done, another thread can't use the same variable, right? If two operations must appear indivisible, they must share the same lock. These are some of the examples in different languages. So basic takeaways that we have is atomicity bugs happen when you assume grouping instead of enforcing it, right? Then comes the order violation bug. Atomicity bugs are about grouping, but order bugs are about the timings. So an order violations occur when the code assumes that A happens before B, but the program never enforces that ordering. This is not a data race, it's basically a missing happen before relationship. So what is that? So for example, in thread 1, you did an init object. In thread 2, you did use object. Looks fine, right? But it's actually not. So see how it's failed. At time t1, you started init object, and at t3, you finished the init, right? But at some time t2, another thread actually used this object. But at that time, it's uninitialized read, right? So it's gonna throw some error. Thread creation does not imply execution order. So you must explicitly imply the execution order. Why the bug survive in your testing? Because it's a very timing dependent, load dependent, and hardware dependent. A very simple fix can be your thread 2 should wait until unless thread 1 signals the completion. Once the thread 1 say, hey, I'm done, now you can go ahead, then only thread 2 can proceed. You can sequentialize those steps. So I'm not saying like you should always do like sequential step, because that's not very good performance. But whenever you think that there are two steps and they should follow some kind of order, in that case you should make sure that you enforce it. You should not believe that it will happen. You should enforce it manually, right? So yeah, some use cases, language mapping, how is this language? So very good takeaways from this is order bags happen when time assumptions aren't synchronized. So these are all the non-deadlock bugs. The key insight that you learn is like check then use pattern. So the first one that we saw, atomicity, is actually first check then use pattern. The second one is init before use assumption. These two things you should never do. So that way you can eliminate most real world concurrency bugs. I just wanted to highlight these two. Then comes the deadlock bugs, which are actually very visible. Deadlock occurs when you get into some cycle. For example, thread 1 lock A is dependent to lock B, and now lock B is dependent to lock A. You are in a cycle and now this is a deadlock. So the four necessary conditions that deadlocks require is mutual exclusion, hold and wait, no preemption, and circular wait. You can just break any of them and the deadlock will be gone. So this framework survives all the solutions. So how systems should deal with this deadlock? There are multiple ways. First is like lock ordering, which is very practical. Always acquire lock in a global order. Example, order by lock address, acquire lowest to highest lock. This is how kernels and databases survive. They never get into a deadlock situation because of this. So they use this lock ordering. Also, you should avoid hold and wait. Acquire all locks at once under a global lock, right? You should never do hold and wait. It kills concurrency, breaks encapsulation, and very hard to maintain. So you shouldn't do this. You should always avoid this hold and wait. Then comes the very third approach is try lock plus back off. You can do a lock and then inside you can do like this. The very good gain from this is deadlock free, but there are a lot of consequences that you have to go through is like live lock possible, complicated cleanup, and easy to get wrong. Then the fourth is lock free approaches like atomic instructions. Then also you will not have deadlock and high throughput but extremely complex to implement. Live lock still possible, memory recompletion is hard. This is why lock free code is rare and heavily reviewed because this is very complex. Detect and recover. Also let deadlocks happen, detect cycle, restart something, use heavily in databases. This is pragmatism, not laziness. So these are the interview cheat sheet you can go through. I'll put this link below the video description, but yeah, that is what I wanted to discuss. I also have a very good small presentation that I wanted to show. The concurrency trap, how erase conditions. So I was basically working with one of the client and I faced this issue. So I thought it's good idea to discuss this. They had an org. Inside the org there was a free plan where they only allow 5 active flows. So in that organization you can create multiple flows, but in a free org you can have just 5 active flows. The goal was to, in a free trial plan, you should have a strict privilege to maximum of 5 active flows. But in reality, by flooding the system with multiple activation requests, user could actually bypass this limit by just not 1 or 2 but 200 to 300%. The Snowflake query also showed 55 organizations on the starter plan, which they had like more than 5 active flows, which is not good. Logs for every individual request shows that the limit check passing the function, which is the check flow limit, would report a valid count, which is 4 of 5 is used, yet the final count would be wrong. So for example, what was happening before doing the activation, there was an enforcer check which actually checks how many flows this organization is allowed to. So they saw that in the logs, every single flow had the same count, like 4 out of 5 is used. So they still had one allowed. How this happened? So this happened because of the race condition. So for example, at T0, you hit the toggle endpoint and you call the check flow limit. The result you got is 4 out of 5 active and you are now allowed to proceed. The gap is you hit this, right? And the result is you got this. Then you commit a DB update and count become 5 out of 5. But during this gap, another request came and that also checked and it also found 4 out of 5 because of the great timings. Now, then after it also proceeded and committed a DB update and count becomes 6 out of 5. The limit has been breached now. So the time to check or time to use the check and the database update are not atomic. The gap is a millisecond window exists between the check flow limit, read operation and database write operation. The result came that multiple in-flight activation requests can pass the check simultaneously before any of them can update the database count. So to fix that, the attempt first was to keep the database label lock. So for the post race, we were trying to use advisory lock, which actually serializes all the access at the database level for a specific resource. So the logic was if we lock the organization ID, only one flow activation transaction for that org can proceed at a time. Other will have to wait in the queue. This is already implemented in Postgres, so we don't have to do a lot, but we have to make sure we do everything within a transaction because this PG advisory lock was only allowed inside the transaction. The initial result was in the development environment with few concurrent users, it worked perfectly fine. But when we got a lot of application requests from all the tenants, the database advisory lock failed. Why? The bottleneck was while a request waits for the advisory lock, it holds into the scarce physical database connection from the shared pool. A single BG tenant firing 20 requests could monopolize 100% of database connection pool, blocking all the other tenants or organizations from accessing the database for any reason. This is very bad experience, right? You don't want that you throw a lot of, like for example, a lot of cars are coming and you put a checkpoint in between, and now because of this you are seeing the heavy traffic, and that is causing the database connection pool overloaded. So the connection pool got overloaded, and next also throw timeout acquiring a connection, the pool is probably full. So the core insight from this approach was the advisory lock correctly controlled concurrency within a single org, but the connection pool is a resource shared, right? It's shared across all the organizations. So we can't go ahead and use that because that is impacting every single organization which are not even related. Using the database for application level queuing is very unscalable. It scales with the number of available connections, not with the number of requests. So we had to remove this. Then we went ahead with the next approach, which is moving the lock up to the stack with the Redis. The tool Redis based distributed lock using redlock algorithm. A unique lock is created per organization, so we created a key value. So the key will be the Redis lock and the value will be this. The behavior, it fails fast. Instead of queuing and holding a connection, if the lock is busy, the server immediately returns 422 another operation is in progress. The safety is like the short 500 millisecond time to live on the lock ensures that if service crashes mid-operation, the lock is atomically released, preventing the permanent deadlocks. So how it actually works? The user requested an operation, they set the lock first inside the Redis. Redis will say, okay, I'm good. Then fetch one of the critical section inside the lock. So check the limit will happen here. You will check the limit. Then you find, okay, how many like check the count. You got the count, update the status, do all this. Once you're done with this, you saw, okay, we have a limit, you updated this, now you can release the lock. After that, in phase 2, you can do all the side effect, like doing some kind of anything extra like webhook registration, deregistration, or anything as such. If there is another lock or another acquisition is in progress, you will directly get 422 another operation is in progress, and you can't actually use this. And this is also up to just one organization. Any other organization can use it at the same time, right? So the two-phase pattern, minimizing the critical section. So this also makes sure that we are not waiting for a long time for the lock to finish. We had a very less time, like 500 millisecond, as I mentioned, as a lock TTL. We can't have more lock TTL because that will the more lock TTL we will add, the more bad user experience will be. Because imagine in the same organization, 5 different people are trying to activate a flow at the same time. Maybe it's a different flow. But since the one person lock is in progress, and if that is for 5 seconds, during those 5 seconds, nobody else in the same organization can actually do that. That was a drawback. So we had to minimize our lock timing. That's why we did all the DB operation inside another phase 1, and all the extra, like the event, maybe you want to send some event to your like Datadog or somewhere, or you want to register a webhook or deregister a webhook or anything like third-party API call or whatever. Everything should be in the phase 2. And if phase 2 fails somehow, you can always revert the phase 1. Okay, so the phase 1 complete, phase 2 begin, webhook registered. If webhook fails, you can compensating transaction revert the DB status. If not, you can set the success. So during the phase 1, when the DB update is complete, you added a flag. We add a flag saying, hey, this is DB update is done. And once you see that the webhook registration failed, here you check, is the flag true? If the flag is true, that means you've already updated the DB. Now you want to revert back because DB, the final operation, which is a webhook step, is not fulfilled. Under the hood, the configuration and code refactoring was very less. So instead of applying transaction around a lot of files, we just did a Redis lock. There was an async waterfall that we converted into DB only step and perform webhook operations. Yeah, so these are all the case file investigated and rejected. Other alternative like use select for update, a row label database lock. Why rejected? Because it suffers from the same connection pool exhaustion problem as advisory lock. Also require a huge intensive refactoring of the application ORM that we were using. Database counter table, we could have a new database table just to track the active flow count, which would be locked on update. Why rejected? Because high overhead, require DB migration, and add complexity of the managing backfilling a new table for a single feature. Post activation reconciliation random delay. This was the worst idea I got, that we can add a random delay in our request and that will actually fix this. This is not gonna fix it. This is just a mitigations, not the solution, and we never go with those things. They don't fix the underlying race condition, they just reduce the likelihood of it happening. Lessons from this is like, don't queue on the database. Your shared connection pool is very finite and critical resource. Using it for application level queuing create a single point of failure. Never ever do that. Always fail fast, don't hang. It's better to reject a request immediately with a retriable error than hold the system resource and degrade the performance for every user. Narrow your lock scope. Whenever you use lock, make sure you narrow down as much as possible your lock scope. Your TTL of the lock should be very minimal. Isolate the input-output from a critical section. Never perform slow, unpredictable network or third-party API call while holding a lock. This is the primary cause of contention. So this was all from my side for today. Hope you liked this lecture. If you liked it, please subscribe the channel. Thank you so much. Have a good day.